All right. In this video, um, I'm going to solve the problem, in the chapter 3.3, Newton's heating and cooling problems. So, as you can see that I want to solve this problem. Um, that's the problem about Newton's the law of heating and cooling. So the problem is this: warehouse is being built that will have neither heating nor cooling. Depending on the amount of insulation, the time constant for the building may range from 1 to 5 hours. So to illustrate the effect insulation will have on the temperature inside the warehouse, assume the outside temperature varies as a sine wave with a minimum of 13 degree Celsius at 2 a.m. and a maximum of 31 degrees Celsius at 2 p.m. So assuming the exponential term, which involved the initial temperature T0 has died off, then what is the lowest temperature inside the building if the time constant is 1 hour? And then if it is 5 hours, and then what is the highest temperature inside the building if the time constant is 1 hour and if it is 5 hours? So so now the so first one we need to start from the differential equation, uh, they governed by the Newton's law of heating and cooling. Okay, so give me a second. Yeah. Oh, excuse me. Oh, it's blurry. So what happened? A second. Yeah, sometimes the autofocus of the webcam doesn't work well. So oh, give me a second. Okay. All right. So the differential equation of heating and cooling is this: dT over dt is equal to k times m of t minus t of t, and then plus h of t, and then plus u of t. Okay. So the m is the outside temperature function, and the T of T is the temperature of the object, okay, or a temperature medium, okay, or in this problem, the temperature of the inside building, okay, and then H of T, this is additional heating source. The U of T is a furnace or AC, heating or cooling source from the furnace or AC unit, okay. So the K is the constant. Normally, the given problem, or you have to figure out K for given condition in the problem. All right. So the problem says that well, the warehouse is being built that will have neither heating nor cooling. So U of T must be 0. Okay. And then they don't mention anything about the additional heating source, so heat source, so H of T must be 0. Okay. And then also the problem says that assume the outside temperature varies as a sine wave. So that means m of t can be expressed as the m0 minus b times and then cosine and then omega t. Okay, so here m0 is the average the outside temperature. Okay, and then b is the amplitude of the wave function, and then omega is what the determine the what period of the sine wave function, right? So let me write it down. So give me a second. So m is the average. Okay, and then b is the amplitude. Okay, and then omega is the period. Normally, normally omega here omega is defined by pi over 12. How can you know that? Because the problem says that um what the let me see. Okay, outside temperature with the outside temperature varies as a sine wave with a minimum of 13 at 2 a.m. Okay, so it means that if we just since the cosine is the wave function means that when omega t is equal to 0, cosine going to be 1, and the omega t is when omega t is pi, cosine going to be minimum value, which is -1. So um, the definitely m of t, I mean the outside temperature will have a minimum value when cosine t has a maximum value because of negative sign right there. This makes sense. Okay. So is it okay? So now then the when t to get the 0, I mean what to get the maximum value of cosine t must be uh 0, right? T equals 0 at oops, I'm sorry, the offside. So time is what 2 a.m. and at t is equal to 0. When t equals 0, we're going to get cosine 0, which is 1, which is a maximum value of cosine. Then m of t going to have minimum temperature, right? So here, then m of 0 going to be m0 minus, and then b times and 1. Cosine, because cosine 0, 1, okay? So this is m0 minus b. That must be equal to what? 13. Because problem says that what the outside temperature with a minimum, I mean, sine varies as a sine wave with a minimum of 13 at 2 a.m. Okay, so t equals 0 means that 2 a.m. And then 2 p.m. the outside temperature gonna have maximum value. What's the duration between 2 and 2 a.m. 2 p.m. 12, right? So to get the 2 p.m. from to get the 2 p.m. to be that time is 2 p.m. reach 2 p.m. then t must be 12 because 12 hours difference between 2 a.m. 2 p.m. right? So m of 12, you see, must be equal to m0 minus. Look at this. Then m of 12 should have maximum value, which means that cosine should have a minimum value because of negative sign right there. Okay, so when does cosine have the minimum? I mean the the minimum value. When cosine gonna have minimum value when omega t gonna be the pi, right? But t is already determined as 12. Okay, so the w times 12 should be pi. That means w must be pi over 12. Does that make sense? Okay, w times 12 is equal to, should be the pi, because cosine pi is -1. Okay, so now then, okay, so now then cosine pi is -1. So wt is equal to, must be, I mean, wt must be pi, and t is 12, then w must be pi over 12. So then b, not minus b times -1, right? Because -1 right there, because cosine pi is -1. Then this is equal to m0 plus b. So m0 plus b then must be equal to 31 degree. Okay, that's why omega must be pi over 12. Okay, so now let me see, and then using, see that we got the system of equation for m0 and b. So solving the system of equation, linear equations of m0 and b, then we get this. M0 is equal to 24. Oh, not 24. I'm sorry. M0 must be what? The 22, right? Because let's see. Yeah, 22. So M0 must be 22. Okay. Then B must be what? Let me see. 9, right? Okay. So we figured out M0 and B. The next one, so we're gonna plug in MT into right there. I mean, let's see. Eventually we have to solve it, right? But yeah, we solve it, right? So I'm going to use the method of integrating factor. Why? Because this is the first order and linear the differential equation. Okay. So, but let me rewrite this one as a standard form of linear differential equation. Then we'll get this dt over dt. Okay, and then plus k times t. Let me skip writing the parenthesis and independent variable t. Okay, so this is equal to k times m right there. Okay, so use, do we know m, right? M is what? M0 minus b times cosine omega t, t minus. So use the integrating factor, use the method. Okay, so then mu, integrating factor mu going to be e to the integral kt, kdt, right? So which is e to the kt. Okay, and then t of t, so solution function, I mean general solution going to be e to the negative kt and the integral, and then mu, which is integral factor, which is e to the kt times m, which is 22 minus 9 times cosine omega t. Okay, t, and then dt, then plus c. So now this is equal to e to the negative, sorry, so e to the negative kt. Okay, and the 22 times in the integral, and the, well, I'm gonna break up this integral, okay, into two partial integrals. Okay, so 22 times e to the kt dt minus 9 times integral e to the kt. Okay, and then cosine omega. Omega is a pi over 12. So let me plug in pi over 12 into the w. Okay, t dt and then plus c. But by the way, when you look at the problem, the problem says that assuming the problem assumed that the exponential term which involved the initial temperature T0 has died off. It means that the what the C must be 0. We assume that C equals 0. Okay, I mean exponential term. This is exponential term, right? Exponential term involve the C. So when you distribute e to negative kt, we're gonna get the c times e to negative kt. This is the exponential term involving initial temperature T0. Okay, because c gonna be c represent the initial temperature T0. Okay, so the problem is that that term has died off, which means that we ignore that. Okay, so the general solution gonna be 22 e to the negative kt times, okay, and then 22 times e to the kt dt, okay, minus 9 times integral e to the kt, okay, and then cosine, and then pi over 12t, again dt. Okay. So the thing is this, it's not a big deal to evaluate the integral, but what about this? We have to use some the integral the special technique for integration, right? So when you look at the integrand, this is the exponential function. This is a cosine function. So integrand is integrand is consistent of the product of two different type of functions. Then you may have to use the integer by parts. So yes, actually you got to use integer by parts. Okay, you apply integer by parts twice actually. Okay, so I'm not going to show that how to evaluate how to apply the process to get the to figure out this integral applying the integer part twice. Okay, this is kind of a long process. So, but when you do this, then you will get this. That is equal to. So this is equal to. Now, I mean, but what about the first term? This is going to be 22 times 1 over k times e to the kt times e to the negative kt, isn't it? Okay. All right. So e to the negative kt, e to the kt going to be, cancel them out. I mean, it becomes 1. Right. So we got 22 over k. Right. Okay. And then minus actually 9 times e to the negative kt in the integral and the e to the kt times cosine pi over 12t in the dt, right? So anyway, so then do this. I mean, applying the integral part twice here, I told you, and this is going to be equal to 22. Okay. Then minus 9, okay, times, all right. So and then, yeah, so in the cosine, let me use a w instead of pi over 12, okay, so for convenience, okay, plus omega over k, okay. The sine, sorry, sine omega t over, and then 1 plus omega w over k and then square, okay. So now and this is equal to, yeah, so okay, so now the problem is this, in the question you can see in the question it says that what is the lowest temperature inside the building? If the time constant is 1. What's the time constant? Here, time constant is 1 over K, right? The constant is the 1 over K. Okay, okay. So first question, they assume that the question 1, they assume that let what time constant is 1 hour. It means that 1 over K is 1. So it means that what? K is the 1, right? Okay, K is 1. Okay. So then, yeah, so, okay, what is the lowest temperature when K is 1? Okay, now how can you find the low temperature when K equals 1? Even we, even though we figured out K, what it is, so that we plug in 1 into K right there in general solution, here, okay, omega. But to find out the lowest temperature, we have to find out the, what? The absolute minimum of T, right? To find the absolute minimum T, we have to find the derivative T. Okay, maybe we have, why? Because we need to apply the first derivative test or the second derivative test, but to use the second derivative test, that we have to take a derivative T and twice, so nobody want to do that. So yeah, we got to apply the first derivative test in calculus 1, but very in the first derivative test, very first step is to find the critical value of T. Right? Anyway, we have to find, we have to take a derivative T, right? So, but yeah, that's good. Yeah, definitely that will work. But I suggest to that we rewrite this one as the let's say, let me see, as the amplitude. I mean, just amplitude times wave function involving phase function. What is this? I'm going to introduce this one. A times, so goal is here. What I want to do that is to rewrite this one as just one single wave function. Okay, so cosine or sine. Okay, it means some amplitude times a cosine function or amplitude times a sine function. Why? Then we can figure out the maximum minimum easily. Okay, because we know the maximum of sine or cosine is 1, minimum of sine and cosine is a negative 1, right? Then we don't have to find out derivative of the general solution T. Again, we don't have to apply the first derivative test. So okay, so this one, give me a second. The first one is what? So first we start this cosine x minus y, okay, is equal to cosine. This is the one of the trigonometric identity. Okay, so cosine x minus y is equal to cosine x times cosine y. Okay, then plus sine x times sine y. Okay, then and then just keep in mind this, and then we're given the sum of wave functions a times cosine omega t plus b times sine omega t. This is equal to, all right, first one, we're gonna the rewrite this one is like this, r times a over r, and then cosine omega t, let's say omega t, and then plus b over r times sine omega t. Okay. Oop, can you see that? Yeah. So what is r? The r is uh, uh, the square root of a squared plus b squared. Okay. So now then, that is equal to r times. Okay. Okay. So now, okay. So first of all, let's figure out the relationship between a, b, and this guy. So what that means? Actually, r is the square root of a squared plus b squared, which means that we can explain, we can figure out relationship among the, I mean, we can figure out the relationship among a, b, and r in the right triangle with the, let's say, angle, no, let's say delta, okay? Then let's say this is a, and this is b, then this is going to be r, right? Because by Pythagorean theorem, the length of the hypotenuse is going to be square root of a squared plus b squared, right? So this is r, right? Okay. Then, so a over r going to be what? A over r, that's going to be cosine, right? I told you this is cosine. Sine is b over r. Cosine is a over r. And tangent is what? The b over a, right? Okay, keep in mind this. So a over r is nothing but what? Cosine delta. Okay, cosine delta times, and then cosine omega t plus b over r is what? Sine delta. Okay, times, and then sine omega t. Okay. Okay, so now I'm going to use that trigonometric identity. Cosine x times cosine y plus sine x times sine y going to be what? Cosine x minus y. So applying this one, applying this one into here, we're going to get r times what? Cosine omega t minus delta. Does it make sense, right? Okay. So I'm going to use this technique, okay, in here. Okay. So now that by the way, so now then yeah, that one we're gonna see this. We're gonna see this technique. We're gonna use this technique the later section in chapter 4. Okay. So keep in mind this. And then what was the general function of the differential equation of heating and cooling problems? That was the m0 and then minus b, okay, times cosine omega wt plus w over k, and then sine wt over 1 plus w over k squared, right? So this is equal to m0 minus b, right? Okay. Then what? Let me see. What was the previous one? M0. And then, one second. Okay. 0 C 0. Yeah. It's gonna be A B. Okay. So now the M0 B times, and then 1 over, I mean, yeah, 1 over 1 plus omega W over K square times cosine WT plus, what I'm doing is I'm just breaking up this fraction into two partial fractions, okay? So W over K over 1 plus W over K squared, and then times sine WT. Okay, so we can consider this one as A and this one is B. Okay, and then R going to be what, square root of A squared plus B squared, right? Which is the taking a square, then we'll get the 1 plus W over K squared to the negative 1/2. Okay. So now then, let's see here. Okay. Okay, 1 plus here. All right, now next one is this. Let's see. So this is equal to. Give me a second. Yeah, so this is equal to then 1 plus W over K squared to the negative 1/2. Okay, and then times cosine, right? And then cosine omega t minus delta. Okay. All right. So now then, m0. I'm sorry. Let's see. This is equal to m0 minus b times. Okay, m0 minus b times. All right. So the what's the maximum here? The maximum of t. We're gonna get maximum t at what? At t is equal to what? So when what time we're gonna have maximum temperature t? Cosine omega t minus delta gonna be when cosine of omega t minus delta equals 1, we're gonna have the minus 1. We're gonna have maximum because of negative sign, right? So because we don't know what's delta. Okay, we don't know what's delta, right? So we cannot figure out as of now we cannot figure out the specific value of time t, so that cosine wt minus delta equals -1, but definitely we know that cosine wt minus delta should be -1 to get the maximum value maximum temperature. Okay, so at cosine wt minus delta is equal to -1. Okay, then maximum of the maximum temperature T, this is must be what? M0 plus B times 1 plus W over K square to the -1/2. And the minimum going to be minimum temperature T, this is equal to what? M0 minus, this will happen, we're going to get the minimum temperature T when what? Cosine WT minus delta is equal to 1. When cosine WT minus delta equals 1, then we're gonna get M0 minus B, right? So M0 minus B, times 1 plus W over K square -1/2. Okay. So applying these two formula into problem, we can find out the maximum temperature and the highest temperature, lowest temperature at specific time constant. Okay, so in the first question was what? Let's find the high temperature and the lowest temperature when k equals 1. So we're going to plug in 1 into k. Okay, so then when the maximum t is going to be what? 22 is a 22, right? 22 minus plus 9 times 1 plus W is a pi over 12, right? And then K is what? 1, right? And then square and then -1/2. Okay. So you can figure out decimal expression of this one using calculator, right? It's not a big deal. And the minimum temperature gonna be what? Lowest temperature gonna be 22 minus 9 times 1 plus pi over 12 over 1 and square to the negative 1/2. Also, we can figure out decimal expression using calculator. Okay. Similarly, we can solve. You can solve the you can figure out the answer for other questions applying that formulas. Okay. So that's the that was the application problem uh, of the first order differential equation regarding to Newton's law of heating and cooling. Okay, so I'll stop here. Okay, excuse me. I hope that this is gonna be help to solve problems, other problems. Okay, so let me stop here.